Today I am going to discuss about the heat treatment of steels. So here, why we are doing the heat treatment for the steels? Normally when you need to change the properties of the material, so we go for this kind of treatments. So first you should know what do you mean by heat treatment. The heat treatment, it is defined as an operation or the combination of operation which involves in heating and cooling of metal or the alloy in its solid state with the objective of changing the characteristics of the material. That means the heat treatment process. So we are going to heat the material, otherwise we are going to cool the material. Okay, so sometimes it is going to involve both the processes. So sometimes it is going to involve only one process. That is why they are saying it is a operation or a combination of operation which involves the heating and cooling of a metal or the alloy in its solid state. So that we are going to change the characteristics of the material. The amount of carbon present in the plain carbon steel has pronounced effect on the properties of the steel and the selection of the suitable heat treatment to attain the certain desired properties. So normally the steel, it is a combination of ferrous and carbon, right? So the carbon percentage, it will affect the properties of the steel. Okay, so based on the percentage of the carbon in the steel, we have to select the suitable heat treatment process to get certain desired properties of the materials. And the steels can be heat treated to produce the great variety of microstructures and properties. Generally the heat treatment uses the phase transformation during the heating and cooling to change the microstructure in a solid state. So when we are going to give this kind of heat treatment process, okay, we are going to change the microstructure of the material, so that we are going to change the properties of the materials. Generally during the heat treatment process, so the phase, it is going to be transformed when we are going to heat or the cool the material, so that it will changes the microstructure in a solid state. So these are the few reasons why we are going for heat treatment process. Normally when we are going to heat any component of the material, okay, it is going to relieve the internal stresses. Okay, so normally the internal stresses which is developed during the cold working process or the welding or casting or forging, so that we are going to relieve during the heat treatment process. And also the material or the component, it is going to become harder, and also it will gain some strength by doing this heat treatment process, and it will improve the machinability, and also the grain size also, it is going to be changed when we are going to supply the heat to the material of the component. And also the material, it is going to become very softer. The metals, it is going to become softer for the cold working process or in wire drawing or the cold rolling, so it will help you. And also it will improve the ductility and toughness of the material. And for increasing heat or wear or corrosion resistance of the material also, we are going to do this kind of process. And also heat treatment process, it will improve the electrical and magnetic properties of the material, and it will homogenize the structure to remove the coring. It will homogenize the structure of the material, and also it will remove the coring. It will sphericize tiny particles such as those the ferrous carbide in a steel by the diffusion. So there is a various stages are involved in the heat treatment process. Okay, normally there is a three different stages are involved in the heat treatment process. In the stage one, the heating is done. Okay, the heating is done in the stage one. Slowly we are going to supply the heat to the metal, so that it will ensure a uniform temperature. In a stage 2, the soaking will be done. So we are going to hold that particular temperature for a certain period of time, so that so it will hold that material for certain period of time at that particular temperature. So at that time the internal structural changes is going to take place. Okay, during the soaking period, the internal structure, it is going to be changed. Normally this holding period, or the soaking period, it will depends upon the chemical analysis of the metal and the mass of the part. Okay, so in the initial stage, in the stage 1 only, we are going to supply the heat to the metal or the alloy. Okay, the continuous, the uniform temperature we are going to supply. After certain period of time, we are holding it for certain period of time at the particular temperature. In the stage 3, we are going to cool the metal to the room temperature. So this is going to be done in the heat treatment process. What we are doing the stage when initially we are supplying some heat to the metal or the alloy. Okay, the uniform temperature it is going to be supplied. So normally for steels we are going to supply the temperature above the recrystallization process. Okay, above the recrystallization, normally high temperatures we are going to supply at that time. So it is going to change its microstructures. So after that, we are going to hold that. We are going to hold that metal at a given temperature for a certain period of time. Okay. And the last stage is we are going to cool down the metal to the room temperature. So to cool the metal, you can place it in a direct contact with the cooling medium, which is composed of gas or a liquid or a solid or the combination of any one of these. Okay. So in the last stage, we are doing cooling, right? For cooling purpose, we can use anything, any kind of medium. Okay, any kind of cooling medium. So we should be in contact directly. So it may be gas, it may be liquid, it may be solid, or sometimes we are going to use the combination of any one of these. So how it is going to transfer during the heating? Okay, under the equilibrium condition, we'll say the transformation of perlite to the austenite. So the perlite, how it is going to be transformed to the austenite? So it is takes place at lower critical temperature of 723 degrees centigrade. Normally the perlite it is going to be transferred to austenite at temperature of 720 degrees centigrade. At this temperature, the perlite it will changes to austenite because of the nucleation process. Okay. Next, transformation of austenite to perlite. So how the austenite next it is going to be transformed to the perlite. This transformation of austenite it will begins with the nucleation of certain platelet at the austenite grain boundary. The diffusion of carbon atoms austenite surroundings the cementite takes place, and the cementite it will be continuous further. So here this diagram it will explain you how it is going to be transformed during the heat treatment process. The austenite carbon contains, okay, so it will convert it into the ferrite. So when the carbon it is going to diffuse, so it will be directly converted into ferrite. Okay, so the same process again it is going to repeat it. So the more carbon rejection it is going to happen, and the cemented platelet is going to form. So below the 72 degree centigrade, okay, normally temperature at 550 degree centigrade, so the austenite directly it will be converted into the perlite. So this is the Tibble tree diagram. Normally we can call it as the C curve or the S curve. Okay, so the Tibble tree time temperature transformation curve we can call it as. During the heat treatment, the austenite how it is going to transform to the various forms. We can observe very clearly in this diagram, the Tibble tree diagrams. So we can observe how the austenite it is going to be transformed to the various forms. Okay, the time and temperature at which austenite transforms takes place has significant impact on a new matter, which is ultimately decide the properties of the material or the properties of the steel. Okay, so this study is done at the constant temperature. Okay, so that is why it is known as the isothermal transformation, because we are studying this at the constant temperature. So that is why it is called the isothermal transformation. This stability diagram we can call it as the IT as well as the C curve or the S curve. Okay, so here these are the different forms of the austenite, how it is going to be changed into the different forms during the heat treatment process. So during the heat treatment process, the austenite it is going to be changed to the ferrite, and also it is going to transform to the perlite and bainite and marstenite and last cementite. So these are the various forms of the austenite during the heat treatment process, that we are going to observe very clearly in the TBT diagram. The TBT diagram you should remember as a time temperature transformation diagram. Okay, so it will significantly impact any new matter which is ultimately decide the properties of the steel. Okay, the austenite, how it is going to transform during the heat treatment process, that it will shows very clearly. So first we'll see the what are the different constitutions of steel and iron. Okay, suppose if you say the ferrite, how you are going to decide it is a ferrite? The iron normally which contains a little or the no carbon is called the ferrite. I told you that the steel normally it is consisting of the ferrite and also it is consisting of the some percentage of carbon. Okay, the combination of ferrite and carbon, you can call it as the steel. Okay, suppose if it is having the no carbon, okay, completely without having any carbon content in the um, material, that iron we can call it as the ferrite. Otherwise the iron which is having the very little bit of carbon, very negligible percentage of carbon, that we are calling it as a ferrite. So in ferrite the maximum solubility carbon is only 0.02% at the 720 degrees centigrade. Okay, so I told you that it is very negligible. So ferrite it is consisting of only 0.02% of solubility of carbon at 720 degrees centigrade. So at stage it is having very soft and it is having the ductile material. Okay, so that we can call it as the alpha iron. The ferrite we can call it as the alpha iron because it is very soft and it is having the ductile property. The second one is cementite. This is a definite carbonate of iron, which is extremely hard, being harder than ordinary hardened steel or the glass. Normally, the cementite is very strong in nature. Okay, normally it is harder than the ordinary hardened steel and the glass. Okay, in this cementite, the 6.67 percentage of carbon it is having. So normally sometimes it is having the 8% also. 6.67% to 8% of carbon it will consist. It's intermediate compound which contains 93.3 percentage. I told you, so depends upon the carbon percentage, the iron percentage it will varies. Sometimes suppose if it is having 6.67 percentage of carbon, so iron it is having 93.3%. Normally any steel if you take, it is a combination of ferrous and carbon. Okay, the majority portion, the main element is the ferrous, so that the majority portion it is consisting of ferrous and the minor portion it is consisting of carbon content. So here the pearlite. The pearlite actually it is a mixture of ferrite and cementite. Okay, so 87% of ferrite will be there and cementite 12.5% will be there. So the combination of these two or the mixture of this ferrite and cementite we can call it as the pearlite. Okay, normally the pearlite is a eutectide of steel. Okay, so the fourth one is martensite. This is the brittle mass of fibrous and a needle-like structure, the chief constituents of the hardened steel. And also it is produced by the rapid quenching of high carbon steel from a slightly high temperature than the maximum temperature of critical temperature. So here this kind of martensite, how we are going to get it means, initially we are going to heat it. So if you heat the material, which kind of material which is having the high carbon, so the high carbon steels we are going to heat and suddenly we are going to cool down. Okay, initially we are going to heat the high carbon steel at the high temperatures above the critical temperature, and then again directly we are going to cool down. So the rapid quenching is done so that we are going to get this kind of martensite material. Okay, this martensite material normally it is brittle in nature. Okay, and also in structure it look like a needle. The fifth one is austenite. The solid solution of gamma iron we can call it as the austenite. Normally when carbon steel with more than 1.1% carbon, So we are going to get this kind of austenite. So normally when carbon steel, we are going to heat at the 1145 degrees centigrade above the critical temperature. Okay, and suddenly if you cool down that, so we are going to get this kind of austenite material. The last one is a binate. So it is formed from the austenite in temperature range below the 530 degrees centigrade. It's like a perlite mixture of ferrite and iron carbide, but in different form. It's harder and tougher and stronger than ferrite perlite. So this binate we are going to form when you are going to heat the austenite above or below the critical temperature. Normally 530 degree centigrade below, if you heat, we are going to get this binate. Normally the binate, it is a perlite mixture of ferrite and iron carbide. Okay, and it is very hot and it is very tough and it is very strong than the ferrite and perlite material. Thank you.